Next, go to the example to know intuitively what is the isolated singular point. The first example, we have the function f of g, which is equal to g negative 1 is divided by g to the 5 times g squared plus 9. Okay, this function has the 3 isolated singular points, which means that is we know that isolated singular point makes the denominator 0. So here we consider denominator g to the 5 times g squared plus 9 is 0, means okay, here g is equal to 0 and g is equal to plus minus 3i. Okay, this comes from this, and this plus minus 3i comes from this. So this function has 3 isolated singular points. In general, singular points of a rational function or quotient of two polynomials are always isolated. Okay, let's check it more closely with this example. There is a 3 point 0 and okay, we have plane, complex plane. So we consider real and imaginary part, axis, I mean. Here is G naught, the origin, and plus minus 3i, 1, 2, 3, 3i, and negative I here, 1, 2, 3, negative I here. Okay, here is 0. There is enough space between 2 points here and here for any pair of points. So we can have a epsilon ball here. Isolated can be defined with this deleted epsilon neighborhood, which is given by this in the form of this. Okay, so for any point, one of the 3 points here, we can make deleted epsilon neighborhood here. Here a singular point 0 or plus minus 3i, such that f is analytic. Okay, here is the given function. Here f of g is equal to g negative 1 divided by these terms. For any point here, there is no point makes the denominator of f of g 0. So which that is analytic at any point epsilon neighborhood disk. Here delete epsilon neighborhood here. So singular point here at any singular point is isolated. yeah, it is easy to see that. However, we can generalize this case. In general, singular points of a rational function or quotient of two polynomials are always isolated because the zeros of the polynomial in the denominator are finite in number by the fundamental theorem of algebra, which is described in section 58. Do you remember? Yeah, we have this theorem, but we skip the part without go through the details. But it is quite important theorem. So let us check it briefly here. The fundamental theorem of algebra in section 58 says here, any polynomial p of g is equal to a0 plus a1g plus a2g squared plus an g to the n, where an is not equal to 0 here, which means that degree it has a degree n. Here we assume that n is greater than or equal to 1, has at least 1 0. That is, there exists at least one point g0 such that p of g0 is equal to 0. This theorem can be proved by using Liouville's theorem, which is given in section 58. Actually, the proof is given by contradiction, in section 58. Intuitively, the fundamental theorem tells us that any polynomial p of g of degree n, here we assume that n is greater than or equal to 1, can be expressed as a product of linear factors. We can see here p of g can be expressed as the product of linear factor here, g negative g1 times g negative g2 and g negative gn here, and has some coefficient c and gk are here complex constants. So any polynomial can be divided into linear factors here. So if we consider the zeros of polynomial in the denominator here, the zeros could come from here, linear factor. So there are, let's just check it more precisely here. The fundamental theorem ensures that p of g has a 0 g1. Here we are going to check how come we can derive this product of linear factors. Okay, first, the fundamental theorem ensures that p of g has a 0 g1. Then we are applied the result of exercise 8 in section 59. According to this result, we have this. Your p of g is g negative g1 times q1g. Here q1g is a polynomial of g of degree n negative 1. degree is less than 1, yeah, compared to the original polynomial here, p of g, I mean. So we have this, yeah, it's a factorization. And then we can use a similar argument, actually same argument, applied to Q1G here. Here we start with the P of G, polynomial P of G, but next we do same thing with the polynomial Q1G here. Then we have a same result, which means that we have Q1G is equal to G negative G2 times Q2G. Yeah, here Q1G has a linear factor with some Q2G polynomial of degree n negative 2 here. So in this way, we can continue to factor the polynomial, the original polynomial P of G to get this here, which is equal to C times C negative G1 times C negative G2. Yeah, keep going like this, and G negative Gn. Of course, here some of the constant G sub k here, yeah, could be identical. However, it is clear that P of G can have no more than n distinct zeros. Okay, and must n distinct zeros. Yeah, we get this from this factorization here. So we'll back to the example here. The zeros of polynomial in the denominator are finite in number. We have just checked it by fundamental theorem of the algebra. So the singular point of rational function, given by this form, the polynomials for one polynomial is for numerator and the other polynomial is for numerator here, are always isolated. Okay.